In this problem, folks, we're going to talk about range. And range in a projectile basically means how far a projectile is going to travel. Now, if it's really interesting, if you're trying to shoot a projectile the maximum horizontal distance or have the greatest range, there's always a very classic physics question: what is the best angle? If you shoot it at a shallow angle, like 30 degrees, you're going to have a large horizontal velocity, but the vertical velocity is going to be small enough so that it's not in the air for very long. If you shoot the projectile at a bigger, like a 60-degree angle, it's going to be in the air for a very long time, but you are going to have a smaller horizontal velocity. So what is the optimized angle at which you should shoot a projectile? Well, the optimized angle mathematically is about 45 degrees. And that 45 degrees is because it maximizes your horizontal velocity and maximizes your time in the air so that you end up with the furthest range. Of course, that is if we can ignore air resistance. And we can get away with ignoring air resistance only for small projectiles that are not going very far and they happen to be real smooth. A friend of my husband's happens to be a former artillery officer in the Army, and he has told me that it has to be a lot lower than 45 when you actually do shoot off an artillery shell, because of the fact that there is air resistance and you don't want it to be too high in the air because it increases the quantity of friction. So the book actually says the optimum angle in a real missile or artillery situation is about 38 degrees. But in our problem, we're going to stick here with 45, and we're going to use an equation that we have not used before. And this is in your OpenStax textbook, and this is the range equation. So let's take a look at that. The range equation says that the range, which is equivalent to the horizontal displacement, is going to be equal to the original velocity squared times the sine of 2 times theta. So you have to take whatever you get for an angle, multiply it by 2, divided by the acceleration of gravity. Now this equation can be derived using all of the lovely kinematics equations and trigonometry we know, but this is handy sometimes. So let's go ahead and use this. A football player punts a ball at a 45-degree angle, so that's going to be my theta, 45. The ball travels 60 meters. That's going to be my range. And I want to know with what velocity the ball left the punter's foot. So I don't know the original velocity that is shot off at this 45-degree angle. So let's go ahead and do some algebra. I want to solve for V. So in order to solve for V, I am going to multiply both sides times the acceleration of gravity. That's going to reduce that. And then to get V alone, I'm going to divide both sides by the sine of 2 times theta. So divide sine of 2 times theta. That's going to cancel, and that's going to leave me with original velocity squared. So let's simplify this. Original velocity squared is going to be my range times the acceleration of gravity divided by the sine of 2 theta. And how do you undo a square? You undo a square with a square root. So that's going to give me my original velocity off the foot of the punter. So in this problem, the range was 60 meters. Acceleration of gravity, 9.8 meters per second squared. The sine of 2 times 45 degrees, and then we're going to take the square root of absolutely everything. Now when I throw this into my calculator, make sure you take 2 times 45 or 90, then take the sine, divide that into 60 times 9.8 square root. My original velocity when I calculated it, my goodness, it was kind of getting disco-y there. The original velocity that I calculated was 24.2, and then let's take a look at units. Meters times meters per second squared gives me meters squared per second squared. When I take the square root of that, meters per second. So that's that range equation. It's really handy now and then. All right, see you later. Bye-bye.